The next topic that we're going to talk about is the LZW encoding algorithm. And this LZW encoder uses what is called a fixed word length encoder. What LZW does is it converts strings of symbols into integer codes. And decompression essentially converts codes back to strings. This returns the same text. So what is the fundamental property is that it tries to find the longest possible string that we have a code for. Okay. Then outputs that string. Okay. At the heart of it is a dictionary. This is somewhat like let me give you an example. Okay. Suppose we have 1000 x's followed by 2000 y's in a string. Assume 8-bit ASCII. Then number of bits required to represent the string will be 1000 into 8 plus 2000 into 8 plus 2 bytes for end of string or end of whatever. Okay, \0 for that matter. So you need end of string. In C, for example, this is represented by \0, so you require 2 bytes for this. So this will be 3002 bytes. Will be required to encode this. Now suppose we use what is called run length coding. Thousand x 2000 byte. It's 10 characters long. And so you need 10 bytes to represent this, plus the end of string, 2 bytes, you need 12 bytes. But of course, you should have an appropriate decoder. Appropriate decoder is required. Okay. All right. So you can, you can even the run length, for example, can also be included. For example, suppose you allow 2 bytes, then you require for each run length, you require 2 plus 1, 2 plus 1 plus 2, 8 bytes to store the entire string. Okay. For example, what I'm saying is if you use only 2 bytes to encode the run length, that means 1000, 2000, that means you can have up to the power of 16 is your max run length. Then you only need 8 bytes. So essentially, this is just to give you an idea of how compression can be much better achieved. LZW is something like this. So what is it, this run length coding, what is it looking at? It's looking at some repeated pattern, right? It's saying that the pattern repeats itself some 8 times and then it reduces the code length. So what we do is, as I said already, maps strings to strings of text into numeric codes. That is the fundamental property. Okay, let's see how we do this. Initially, we assign all the characters that occur singly. Well, I'll tell you what I mean by it. In the text, a code. For example, suppose we have this string have triple A B B B B B A B A. There are only 2 characters, 2 unique characters. So what we first do is we assign A the code or numeric code 0 and B the numeric code 1. This mapping is stored in a dictionary. Now, the Huffman code is also stored in a dictionary, but there is a fundamental difference. Okay, what is the fundamental difference that we see here? As opposed to the Huffman code, there is no prior information that is required. In Huffman coding, we needed the probability of occurrence of the letters. Huffman, we needed probability of occurrence of the letters. Okay. In the text, this is something that we require. Here we don't require it. Okay. Let's see how this mapping gets done. The way we do this is the following. So let's see this code over here. I'm sorry. What do I have here? Let us try. Let's see what LZW does on this example. Again, AAA B, 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 B. 5B is A. The point is repeated patterns are very important for the this compression algorithm, and it works extremely well for text files. Okay, so what do? We have the code. So what we do is, interestingly, this one depends a lot on prefixes. It wants the code to be the prefix. looks at the most common longest prefix that it can find. Okay, it tries to find the longest prefix P of the unencoded part of the input file. Okay. Find the longest prefix P of the unencoded part of the input file that is in the dictionary and output its code. Its code. If there is a next character, C, then it makes PC the prefix T. Okay. Then, so basically, if PC not in dictionary, add to the dictionary. That's what is done. So let's look at this example. So now when you look at this example, when you look at this particular example, the longest prefix. So what did we do? We have 0 is A, 1 is B. So let us try this. The longest prefix of the input that is in the initial dictionary in this case is A. Its code is 0. So you output 0 and the string A is assigned the code 2 because it's not there in the dictionary. Put it in the dictionary. You only output the code for the first symbol. Okay. A is output. Then A is output. A is, so you output 0. Then you put insert in dictionary. Okay. Then output. Now next, what do you see? Now this is still the unencoded part, right? You only encoded this fellow. Now you notice this, the longest prefix is this guy. Okay, but that is already in dictionary. And then add this B to it. Put A, B into the dictionary. Now you output the code. Output, put A, B into, insert into the dictionary. Okay. All right. So B is still, notice that we have output only 2. B is there. Now the longest for this is the unencoded part. So where are we now? We are here. This is the unencoded part. Now the longest encode, okay. All right. Then what we do is, now next what do you have? The longest code in the string starting with B is 1. So what do? We output 1. Okay. 1 minute. We add, B is already in the dictionary. So P is already in the dictionary. So we output output 1, 1 is output, and then the longest prefix not in the dictionary is BB. So you insert in the unencoded part in dictionary. So what have we done? We have output the code for the first B, and now what do we see? We see two B's. It's already there in the dictionary. So now you add BBB, insert, sorry, you output BB, and what do we have now? Then you output the code. Sorry, I forgot to put this here. I 4 here. I put BB over here. Okay, let me repeat this again. So we saw A, B, then B is already in the dictionary. B is already in the dictionary, so I output 1. Then the longest string, which is not yet being processed, is BB. I have only output the first B. And after outputting the first B, what do I see? I see 3 Bs. So I can output the first 2 Bs, which is the code 4. Okay. So next, what do? I see BBB is the longest string which is not there. BB is already in the dictionary. I output 4 and, sorry, let me do it in the same form. I output 4 and add BBB to the dictionary. Add to dictionary. Okay. So where does this go now? This will be 5. BBB. Now, what has happened now? I have processed, I have output here, up to here, right? So this is gone. So now next, what do we see? Did I output? And add to the dictionary, BBB. Okay, I'm missing one thing here. Let me put one more B over here. This is a textbook example. And then what I do now is, so we have output all of this. Now the BBB added to the dictionary. Okay. So what is this value now? This is at location 5. Then after I do BBB, if I take the last symbol of this guy, I get a new string. So what do I do now? 5 is output. I output 5 and I add BBB to add to dictionary. Okay. All right. So I have 5 here. So I get 6 here. BBBA. Now, so the last one here. So I have output 5. So 5 corresponds to what? BBB. Then what do I see? So up to here we have it encoded. And I want AAB. AAB is already there in the dictionary. I output 3. And finally I add AABA to the dictionary. Okay. So when you look at this encoding scheme, what does it give you? The output is, which is 0, 2, and I'll come to the end of the input, 4, 5, 3, and 7. Okay. So there's an interesting way of doing this encoding. Now, if you look at this, these are the way you encode it is, this is A, this is B, this is AA. This is like 0, new symbol, 2, new symbol. This is 1, new symbol. And this is 4, new symbol. And this is 5, and new symbol. Okay. This is a nice way of, this is how the encoding is done. And sorry, if I'm 7. 7 is what? A, B, A. So this is what? 3 and E. So this is how the actual encoding is done. Okay. I will take one more example.